Good afternoon everyone, I am Renu Sharma, Assistant Professor EC Department. Today I am going to start with the next part of Unit 4. Now this is related to ASK, FSK and some techniques related to how we are going to modulate the digital information. So this digital transmission. So till now we have discussed about how the analog signal will be transmitted, how it is modulated at the transmitter side, demodulated at the receiver side. So after that we will discuss now what is digital transmission. So digital transmission refers to the transmission of digital signals between two or more points in a communication system. So whenever signal we are going to transmit, it is generally in the form of analog. First we have to convert it into digital form. Now how this analog to digital conversion is being done, that we are going to discuss in this lecture in detail. So there are three different steps related to ADC, that is analog to digital converter. Like first one is the sampling, second one is quantization, third one is encoding. The conversion of analog to digital pulses is known as waveform coding also, because after the signal is converted into bits, that is ones and zeros, a stream of bits will be there. It has to be converted into electrical signal. Now that will be done using this waveform coding. The digitized signal may be in the form of binary or any other form of the discrete level. Now you can see over here, like this one is the continuous time signal. It will be converted using a codec, that is analog to digital encoding. Now this is how the after line coding the signal will looks like, which is nothing but an electrical signal. Now this will going to travel over the channel, over the wire. Now this is the whole procedure which is showing the operation of ADC from analog signal to digital signal. After this the line coding comes into the picture. So first we will discuss, this is analog signal. Now analog signal is continuous in time and it is continuous in amplitude. So both the time and amplitude, this is this axis will be the amplitude, this will be the time, and it is continuous in nature because it is defined at every instant of time. Now it is applied to a PCM encoder. Now PCM encoder is a kind of digital modulator where three different steps are being there. Like first one is the sampling. Sampling will going to convert this signal into this one, that is discrete in time but amplitude is still continuous in nature, which means that we have to take the samples of this signal at equal instants. Like this is taken at 0, then this will be TS, this will be 2 TS, this will be 3 TS and so on, depending on the time instance over which this signal will be explained. So this is how the samples of this signal are collected, and then as you can see the amplitude is still continuous in nature if you are going to construct an envelope from this particular PAM signal, that is pulse amplitude modulated signal. Now after this, when the signal is constructed like this one, and this is denoted by X and TS, if I am taking this signal as XT, so T will be replaced by NTS, where TS is the sampling time. So this shows that it is the sampled version of the input signal. So that will be the first step. Now second step is the quantizing. Now quantizing is basically you are dividing the amplitude axis into different equal sized levels. You can see now this is been divided into equal size level, and the distance between each level is denoted by delta, that is nothing, it is the step size that plays a very important role in this quantization. The quantized signal is denoted by X, Q and TS. This will be TS and this will be 0, TS, 2 TS, 3 TS and so on. So this is how the quantization will be done. And then let's say it will be defined at 2 volt, 2.1 volt, 2.3 volt, 2.4 volt, at all the voltage level this signal will be defined. Now this will be defined only at discrete intervals like 0, 1, 2, 3 if the step size is 1, 0, 2, 4, 6 when the step size is 2, means the distance between the two levels will be 2. That is dependent on the dynamic range of the original signal. If it is varying till 5 volt, then you have to work with from 0 to 5, you have to divide the axis. You need not have to decide up to 10 volt or 12 volt. So, that is the case for quantization. Now, there are two types of quantizer. First one is uniform, second one is non-uniform. In case of uniform quantization, delta is fixed till the end of the dynamic range, and non-uniform delta is variable, which is dependent on the variation of the input signal. So, that is the case of quantizer. Next one will be the encoder. So, encoder, there is a important thing related to encoder. You have to use, you have to consider the number of bits that will use to encode the input signal. Let us say I have taken V is equals to 2. Now, V is equals to 2 is nothing, means I have divided this label into 2 bits of data. So, when 2 bits are considered, then 4 labels will be there, like 0, 0, 0, 1, 1, 0, 1, 1. So, these are the 4 different labels when 2 bits of encoder is being there. When 3 bits of encoder are there, then there are 16 different combination, 8 different combinations are there in case of 3, 000 to 111. So, that will decide the encoder. That is also related to the dynamic range of the input signal. So, all the things, whether it will be a sampling TS, whether it will be quantization, number of labels division, or whether it will be dependent on the encoded number of bits that you have to consider, all will be directly related to the amplitude and time of the input signal. Now, the output of this will be a digital data, which is a stream of bits, that is ones and zeros. So, this is the digital data. Now, after this, we have to consider any kind of line coding. There are 7 to 8 different types of line coding that exist, means different formats, and you can consider any one of that, and then these bits will be converted to electrical signal. Now, after seeing this, we will see what are the advantages of digital transmission. Since all the signals are originally available in analog form, so why cannot we directly modulate it? Why we have to convert it into digital? So, these are some of the advantages why we convert the analog information into digital. So, first one is noise immunity, more resistive to additive noise as it uses signal generation rather than the amplification. Error detection and correction is being provided in case of digital information, digital transmission, like at the receiver side, whatever bits we have received, it will be used, it will be detected, and it will be seen that what will be the, means parities will be checked. If even parity, even number of ones will be there, then even parity will be added. If odd number of ones will be there, then odd parity will be added. So, this is how the error detection and correction will be there. Now, next is ease of multiplexing. Many baseband signals can be combined and transmitted using TDM. Integrating analog and digital data, integration of analog and digital data, use of signal regenerators. Data integrity is provided, like data integrity is due to the signal regenerator or digital repeater, we require data integrity. Data security is provided using this due to encryption, advancement of digital technology. There are some disadvantages related to digital transmission, like it requires more bandwidth, it requires precise time synchronization between the clock used in the transmitter and receiver. It need for additional complex circuitry for the encoded data, because for encoding we require different types of encoders which are available in the market, and dependent on how many number of bits you want to encode into, like 2 bits, 4 bits, 3 bits. So, depending on that you require a encoder also. So, quality of service can degrade all of a sudden and provide a good to very poor of signal to noise ratio, which is dropped. Now, after discussing the digital transmission, how we are going to modulate the signal if it is present in ones and zero form. So, firstly this 1-0 form is being converted into electrical signal using this line coding. So, this is the input modulating digital signal, this is the carrier frequency, you can see that this is continuously varying signal. This will be the ASK signal. So, ASK is basically nothing, it is on off keying also. On off keying means whenever the amplitude is present, this is a kind of unipolar NRZ type of line coding. When the pulse will be present, there will be output which will be proportional to the carrier signal. When the pulse is not present, then the output will be 0. So this is how this FSK will be done. When this is there, then higher frequency signal will be generated. When 0 will be there, then low frequency signal will be generated. Lastly will be the PSK, that is pulse phase shift keying, where the phase, when the signal will change from 1 to 0 or 0 to 1, then the signal phase will be changed. So that is known as phase shift keying. Now next is the sample speech waveform, that is analog. Now what is sample speech waveform? Speech signal is continuous in nature. It is a one-dimensional signal. It consists, it has been explained on time axis only. It has amplitude and time. So when you want to modulate the speech signal, it has to be, it is a continuously varying signal. You have to consider a portion of the signal. Let's say I have considered this is 1 second of signal, and during this 1 second, from this I have to consider, let's say 1 nanosecond of signal I have taken from this continuously varying signal. Now in this duration I have to consider it as, it is a constant signal, stationary signal. Then it is possible to modulate this signal. So that is the sample speech waveform condition. Now next is sampling theorem. So this is the first operation that is been there in case of analog to digital converter. So in this case there are two things that is involved, two definitions are there. A band limited signal of finite energy that has no frequency component higher than W hertz is completely described by specifying the values of the signal instants of time separated by 1/2 W second. So this is a very standard definition of sampling theorem. There are two definitions, you can consider any one of it. First one is related to the transmitter side and other definition is related to the receiver side. So this is about the sampling theorem. So sampling theorem is basically related to the Nyquist rate, or we can say the Nyquist interval. What is Nyquist criteria? Nyquist criteria, that sampling frequency should always be greater than equals to 2 FM, that is known as message signal frequency. So that is the case when Fs should always be greater than equals to 2 FM. So that is the sampling theorem, or sampling data will be sampling frequency. Nyquist criteria is there. Now low pass sampling is, now this is the filter which will be expanded from -W to W0. This is the amplitude of this, that is G0, this is GF. This will be expanded from -2 Fs to +2 Fs, and this will be the bandwidth of the message signal. So spectrum of a strictly band limited signal, that is GT, spectrum of the sampled version of GT for a sample period of Ts, which is equals to 1/2 W. So now W is basically the 2W is basically the bandwidth of the original message signal which you want to take sample from. So that is the low pass sampling case. Now this is the equation that is related to the sampling, that is G delta F is equals to summation n is from -infinity to infinity G n Ts e to the power -j2 pi n Ts. So that is related to the frequency series representation of the periodic signal, because since it is periodic in nature. Now next is low pass sampling continued. Now this is G delta F is equals to summation n is from -infinity to infinity G n by 2W e to the power -j pi n F divided by W. So this is the equation that is related to the low pass sampling only. So there are three different conditions, like Fs is less than 2 FM, it can be Fs is equals to 2 FM, or Fs can be greater than 2 FM. So this is not considered at any point. It is known as aliasing effect. It raises a condition that is known as aliasing effect. Now, aliasing effect means the whatever samples that are being collected, so these are going to give rise to overlapping of the sample. So, that is loss of information, that is responsible for loss of information. So, that is the aliasing condition. When Fs is equals to 2 Fm, this will be the ideal condition. Fs is greater than 2 Fm, this is desired. This is every time we are sampling, we are going to sample at greater than 2 Fm. So, from the last equation, it is evident that if the sample values g n upon 2 w of the signal g t are specified for all time, then the Fourier transform of the signal is uniquely determined by using the Fourier series of equation. So, because g t is related to g f, that is the time domain version of the g f, by using the inverse Fourier transform, it follows that the signal g t is denoted by this equation. So, now the signal reconstruction, consider the problem of reconstructing the signal from the sequence of sample values. So, GT will be defined by this equation, that is from minus infinity to infinity GF e to the power j2 pi ft df. Now, this will be given by this particular formula. So, that is the signal reconstruction case. Now, next is the original signal may be recovered exactly from the sequence of samples by passing it through an ideal low pass filter, that is been denoted by this particular waveform from minus w to plus w 0, and the amplitude will be 1 upon 2 w. So, that will be an HF transfer function of the particular filter. Now, this is the signal reconstruction. Now, sequence of samples is given by this particular equation. It is passed through an ideal low pass filter. Now, this is basically a reconstruction filter. So, whenever there is a problem of some sampling related to the sampling frequency, then reconstruction of the signal reconstruction filter will be there, which will be nothing. It is a kind of ideal low pass filter only, and its transfer function is 1 upon HF. Whatever we have used at the transmitter side, its inverse will be the transfer function of this ideal low pass filter. So, that will be an analog signal. Now, next this is showing what is aliasing. So, in practice, our message signal is not strictly band limited, with the result that some degree of undersampling is encountered, as a consequence of which aliasing produced by the sampling process. So, this is the case for GF versus F. Now, when aliasing is been done, now you can see that this is the loss of information which is taking place. Now, this is basically the overlapping of the sample. So, spectrum of an undersampled version of the signal exhibiting the aliasing phenomenon. So, that is the case for aliasing when Fs is less than 2 Fm, and it is generally not considered. So, to combat the effects of aliasing in practice, we may use two corrective measures like low pass anti-aliasing filter, and the filtered signal is sampled at a rate slightly higher than the Nyquist rate. So, Fs should always be greater than equals to 2 Fm, which we consider. These are the aliasing effects that you can see. Now, this is passed through a low pass filter. Now, this is overlapping of the samples, and when this is the case when Fs is greater than 2 Fm, this is when Fs is less than 2 Fm, and this is the case when Fm is equals to 2 Fm. So, this is showing that where aliasing has been occurred. Thank you.